Uh, Today's class is lesson number 12. It's continuing for the introductory guidance to the quantum mechanics. Our topic today, we are dealing with two different topics. The first one is briefly mentioning about what is the wave function constraints, and the second one is the packet wave. What is the packet wave? So, starting with the wave function constraints. So as we know in quantum mechanics, like every electron or any system or particle has its own wave function. And this wave function actually is the method or the way to describing this electron behavior and system. So if we are able to solve the Schrodinger equation, then this could be by predicting the value or solving the value of the wave function itself. Then wave function is the way of describing the behavior and the motion of the particle in quantum mechanics. So psi x of t, this is gives information about the wave itself and its amplitude or height, because each wave function or plane wave or wave function has different value in terms of amplitude, height, momentum, energy, etc. Also, there is another ways of dealing the wave function, because wave function substituting to the Schrodinger equation previously has kind of imaginary number, which is I, and if we are describing some real values, in our case is electron, by some which is including some non-real values I, then we have to find some different ways. It was by taking the absolute of the wave function and squared to that value and subjected a result into the Schrodinger equation. This term itself, the absolute of the square of the wave function, described to be as the probability density of the particle. It tells about what is the certainty of finding the particle, in our case electron, at specific position x at time t. So how wave function can be physically useful and meaningful? Maybe in our case here, wave function itself, maybe it would not be useful due to some other mathematical numbers. So we have described using the probability density. But in different system or different aspects, how the wave function itself could be physically meaningful, or when we can say this is wave function. There is kind of conditions and requirements to justify and judge if this is wave function or not. So the wave function, it's kind of solution or root for the function. So if wave function sustain with the Schrodinger equation as it satisfy the Schrodinger equation, which is time dependent Schrodinger equation, if we are substituting the wave function value into this equation and both sides of the equation were satisfied, then this is simply wave function. So it has to be a solution for the Schrodinger equation. The second thing is the continuity. The wave function itself is a continuous function. It's a continuous wave function, and it has to keep always continuous. That's mean if there were some continuity and in some place there's kind of discontinuity and again continuity, this is not wave function. It only has to be a continuous wave function. It has to be only a continuous wave function. In the same manner, the probability density function also has to be also continuous function, but its value ranging from 0 to 1, because maximum 100% its value, which is reflecting the 1, that's mean 100% or 90% or 60%, 50% finding the particle in specific position x at time t. The normalization, one of the condition is the normalization. Actually, normalization comes from the probability and statistical background itself, because a wave function, as also it can be described in terms of the probability density, it has not to pass the value of 1. But for this example, this is showing like wave function. If this is my wave function, it's continuous wave function. If I start to discretize, like making some finite values of the uncertainty position of x over the x-axis, and doing such process for all of this wave function, and if I just multiply, don't look for this integration now, just look for this one. If you are multiplying the probability density, this is square, not 2, this is square. So if you are multiplying this value multiplied by x, that means the probability of finding the particle over this finite position. If you are multiplying this by this and summation over all of this region, the position, or you are taking the integration of this wave function, which is area under the curve, then the result has to be equal 1. What is this meaning? This means if you have wave function, the particle 100% has to be located in somewhere in this wave function, but we cannot tell now where is it located, but it's 100% somewhere here in this wave function. It cannot be other place, it's only in this wave function. So this is what is the constraint for the wave function. Now we are going to describe some new definition in quantum mechanics. It's the packet wave. What is the packet wave? So before we are describing what is the packet wave, let's go for some brief background. In quantum mechanics, as a free particle, we have talked about the free particle in previous classes. Like if there is kind of particle moving over x-axis and we are arbitrarily giving that this particle has zero potential energy, that means its energy doesn't change over x-axis, momentum doesn't change, it has the same wavelength. This value can be named as plane wave. I mean the production of the wave function from the free particle which has zero potential, it is known to be as the plane wave. So the plane wave function described by the wave function solution of the Schrodinger equation. So this is the Schrodinger equation solution for the Schrodinger equation of the free particle. And K here is different than quantum, classical mechanics is not the constant of the spring. It is simply P divided by H prime, which is the momentum, divided by Planck constant divided by 2 pi. And the momentum here is, for the free particle, is a precise momentum. It's precise momentum. That means if it's precise momentum were determined, that there is no way for determining the position of this electron over this wave function or the plane wave, because the uncertainty over the position, it's largely it's infinitely large, that we cannot tell where is the particle is located. And this is one of the terms for the Heisenberg uncertainty principle. From this, the solution of the wave function, if we are assuming that P equal to 0, then the free wave particle, which is the plane wave, would be something like this one. It's have constant momentum. It has constant momentum. It changing over minus infinity to infinity with fixed momentum and fixed energy. then the uncertainty for the position is very large. We cannot tell where is exactly the electron over this wave function. It has the same momentum, and uncertainty for the position is infinitely large, so we cannot determine where the particle is. So how can then we determine the particle in more practical ways? So if we are able to determine at least some region that the free particle most probable to be found around, then we can describe in more practical way, in another way, or in another word, if we are successfully determine some localized region, by this method we can describe the position of free particle in quantum mechanics. So how to do so? If we are take the superposition of many plane waves, not only plane wave, we have in this figure we have showing only one plane wave which has same momentum over varying on the x-axis, infinity, positive or negative. So if we are taking the superposition of many plane wave, the superposition of many of the plane waves with different of wavelength, and with slightly different momentum, we can obtain a single wave that is found within a localized region of space, and it is known to be as the wave packets. So wave packet is a single wave produced from the superposition of several or different plane waves. So consider two waves of the same frequency and amplitude traveling toward each other in opposite direction. When they interact, if the wave are in opposite direction phase, antiphase, at that moment in that specific time they will cancel each other, so there will be no waves. But if the wave are slightly out of phase, they have something different from each other, that wave envelope kind of interesting superposition. So for example, this below waves, consider the blue and green wave forms below. They are slightly out of phase, these green and blue. The red waveform is the net result. This is the addition of these two waveforms traveling over x-axis, then adding amplitude of different wave plane as we are adding those different waves. If larger number of waves superimposed, more converged shape will result finally. Here we have red color wave, which is a result of these two superimposed waves, the green and the blue. But if we are going for more number of plane waves, they are superimposed, then we will finally going to a kind of single form, which is the converged form for the large number of superimposed wave functions. This is just kind of different description for what we have just described before. If we are doing kind of summation for different plane waves, each plane wave they have its specific and distinguished momentum, and each momentum is different than the next momentum of the wave function. As we can see, they have somewhat different wavelength. Finally, we will reach into the wave packet, which has kind of different and changing momentum wave that will result with some amount of uncertainty on determining the position of the particle, because we already not precisely determining a single momentum, rather it's changing momentum which is changing over time, and it has some amount of uncertainty value, and this is called the wave packet. It's the method that we can describe the position for the particle in some localized region. So combining many waves leads to pulse or wave pocket. But the more we add waves, the more the distance between the pulses become larger. As we want to localize the bucket, we need to stabilize the buckets. We will then add an infinite number of waves with a particular chosen amplitude. Like variant number of amplitude, momentum will result with localized region, which is the bucket wave. In another word, like the superposition of the interferences of infinite number of plane waves ends up with single localized region, where delta of x is the probability of finding our free particle in this localized region, and the free particle most likely to be at this region. So since the momentum has range of values, in our case here for the bucket wave, delta p not supposed to be equal 0. It's larger or less, it's larger than 0. And from Heisenberg uncertainty principle, there is now an uncertainty of finding the free particle described by the value of delta of x. As bucket wave moving over time, then we have generating kind of bucket wave, and this bucket wave is, or wave bucket, it's moving over time. This is time 1 and time 2. If you are monitoring this wave, it's changing. That means the electron or the particle which is located in this pulse, it will change its position. Now at time between time 0 and time 1, the particle were at this position. Now between time 1 and time 2, the particle is at this position, and between time 2 and time 3, the particle is at this position. This is how can we simply determine the position of particle through the new term of the waves, which is the pocket wave. Then pocket wave is the superposition of several and infinite number of plane waves. The plane waves, which is the wave of the free particle, and the free particle is the particle which is moving over 1D x-axis with zero arbitrary chosen zero potential energy. And this is briefly our topic. Two topics today is the uncertainty for the wave pocket, and a constraint for the wave function itself has been described. Thank you.